let's now compare the reactivity of acid anhydrides with that of esters in nucleophilic acyl substitution reactions. And again, as we have done before, in the comparison between the reactivity of acid chlorides with that of anhydrides in nucleophilic acyl substitution, we do exactly the same. So we always look at the two issues, the electrophilicity and the leaving group ability. Let's see that. Now, in the case of acid anhydrides, this carbon of the carbonyl group is bonded to oxygen. So obviously oxygen is more electronegative than carbon, which leaves a negative delta on oxygen and a positive delta on carbon. But we have exactly the same here. So there is also inductive withdrawal by oxygen, which leaves a positive partial charge on carbon of the carbonyl group and a negative partial charge on oxygen. So in that, they are similar. But remember, oxygen can donate electrons by resonance. That's because it has lone pairs. So let's draw the lone pairs. Now, two lone pairs in this case, and of course, two lone pairs here as well. So both of them can actually donate by resonance. So let's do that. So let's take that lone pair and make a double bond, and of course break that double bond accordingly. If we do this, we get another resonance form for acid anhydrides. So that's a resonance form. Let's do the same resonance, a very similar resonance on esters as well. So if we do that, we get actually this resonance form. So far, they are not really different, but remember, this oxygen is also bonded to another carbonyl group, which means that the lone pair on oxygen, not only it can be donated to this part of the compound or over, or that lone pair can not only be delocalized, if you like, over this carbonyl group, but also over the other carbonyl group. So we can actually do that as well. So let's do that. So this carbonyl group is reformed, and this double bond is broken. So of course, there was a positive charge before, and then as a result, of course, this carbonyl oxygen bond is broken. So we get now another resonance form. So that's a third resonance form. Now, in the case of esters, that carbonyl group is not present. It's only a simple ester. So therefore, this resonance donation by this oxygen, which is flanked by the two carbonyl group, can be spread over two carbonyl groups. So resonance donation in this case, with respect to that carbon, if we take that as a reference, resonance donation is now actually less relative to esters, because it is spread over two carbonyl groups. So resonance donation is not as strong. Therefore, the electrophilicity, well, before that, electron density is not as high as in this case, and therefore the electrophilicity should be higher relative to that to the carbon of esters. So if you like, resonance donation is spread over two carbonyl groups here. So over two carbonyl groups. So therefore, this carbon is less electron dense. Therefore, it is more electrophilic. Now, this carbon here is actually the electron density on this carbon is actually concentrated as a result of a single resonance donation. So therefore, this is more. It's more electron dense. It is more electron dense. Therefore, it is less electrophilic. So therefore, carbon of acid anhydrides, carbon that's connected or that's carbon of the carbonyl group in acid anhydrides is actually more electrophilic than carbon of esters because of the fact that resonance donation here is spread over two carbonyl groups. Electron delocalization is actually over two carbonyl groups, so it's delocalized if electrons more in this case, whereas here the delocalization is only on one, so there's more concentration of the negative of electron density, so therefore carbon in this case is more electron dense, it's also less electrophilic. We have just seen that acid anhydrides are more electrophilic at carbon of the carbonyl group than esters. That's because of the less resonance donation in this case relative to that. Therefore, electron density here is actually less, and therefore the electrophilicity is higher. So this carbon, therefore, is more electrophilic as we have just seen. What about leaving group ability? Now, if acid anhydrides take part in nucleophilic acyl substitution reactions, then the leaving group would be actually the carboxylate ion. This is the carboxylate ion, and here we would have OR minus, which is the alkoxide. Now, carboxylate ions, as you already know also because they are conjugate bases of carboxylic acids, carboxylate ions are actually stabilized by resonance. So you can actually do resonance to stabilize this conjugate base to get something like this. So another resonance form for the carboxylate. Now this resonance stabilization cannot be done on the alkoxide because there is no carbonyl group, there is no multiple bond nearby. Now, this is therefore stabilization. Yeah, so this is resonance stabilization, whereas such stabilization cannot be done over on the alkoxide. Now, we can also look at the corresponding acids. Carboxylates come from carboxylic acids with a pKa of, in general, 5. OR minus or alkoxides come from alcohols with a pKa of about 16. So obviously alcohols are weaker as acids than carboxylic acids, so therefore the alkoxide ion is a stronger base. So this is actually a stronger base relative to the carboxylate. That's because this is stabilized, the carboxylate is stabilized by resonance, stronger base, therefore less stable ion, therefore it is a worse actually leaving group. Now, the carboxylate is a more stable ion. It's a weaker, carboxylate ion is a weaker base. It's more stable ion because of resonance, so it's more stable, obviously, ion. So therefore it is the carboxylate ion is a better leaving group than the alkoxide, something that's not really new to us because we know this even before when we talked about acidity of carboxylic acids and also when we talked about acidity of alcohols. Of course, carboxylic acids are more acidic than alcohols. That's because their conjugate bases are stabilized by resonance, a fact or a phenomenon that is not present in the case of alkoxides. Now, in summary, acid anhydrides are more electrophilic at carbon of the carbonyl group than esters. Also, acid anhydrides contain a beta leaving group, which is the carboxylate. That's a beta leaving group than the alkoxide ion, which is present in esters. So therefore, acid anhydrides are actually more reactive. Acid anhydrides are more reactive than esters in nucleophilic acyl substitution reactions, not only because of the higher electrophilicity, but also because of the beta leaving group ability.